Okay, so hello everybody. It's Mr. Carr again. Today we're going to be looking at 8-2 day 2. In this scenario, we're going to be looking at representing, or sorry, we're going to write a vector as a linear combination of unit vectors. So let's start looking at what that means. Okay, when we look at our standard unit vectors, we're going to label these as I and J. So here we have 1, 0, which is telling me I'm moving in the X direction to the right. And in J, I'm going 0, 1, which I'm saying is going 1 up. So in this scenario, we're basically looking at I is always going to be moving right to or left to right for my unit vector. So that's I. And then J is going up like this. All right. So from here, vectors can be expressed as a linear combination of these unit vectors. So if we take any vector like AB, like this, we know that we can break it down in terms of like if I'm moving in the A direction, that's going to look like this. It's A, whoops, A comma 0. That's my X component. And then 0 comma B would be my Y component. Okay, so I'm saying that in this case, we move in the direction of, we go in the X direction of value of A, but then we don't move in the Y. So that's moving in just the X direction, and then we're followed by just the Y direction. Okay, so since we can kind of factor out an A here, that's like a scalar of A times 1, 0. And then we can factor out a B here, so it's B times the scalar B times a 0, 1, like that. And then we know from earlier, these two are I and J. So basically, we have A and B is going to be A times I plus B times J. It's just a slightly different way of expressing our vectors here. So if we look at this one, so write a unit vector as a linear combination of unit vectors here. So let DE be the vector from initial point D, -3, -3. So we got 1, 2, 3, 1, 2, 3 here. Here's point D. And terminal point E is 2, 6. So we got 1, 2, 1, 2, 3, 4, 5, 6. Okay, so my vector is doing this motion here. But remember, the vector is moving in both the horizontal and vertical direction. So horizontally, it's going 1, 2, 3, 4, 5 to the right. And then 1, 2, 3, 4, 5, 6, 7, 8, 9 up. So if I'm going 5 to the right and 9 up in this scenario, is going to be, whoops, I don't want red here. It's going to be 5I plus 9J. That is my linear combination because again, I and J are 1, 0, and 0, 1. It's the same thing as this. It's 5, 9. Okay, so it's just linear combination versus component form. That's all. Okay, so let's look at this. Find the component form of this one here. So find our component form of the vector v with a magnitude of 7 and a direction angle of 60. So it looks something kind of like this. I would do something like this. Magnitude is 7. My theta here is going to be 60. So again, if I model that, let's get rid of the dashed line here. If I model that as my x and y components, we have this is going to be in the x direction, okay? And then this is going to be in the y direction. So I'm making a triangle when I make my vector, so I can do my trigonometry here. So when I do that, I'm going to look at in terms of, let's go with x first here. So x is going to be adjacent, and this is hypotenuse, so we're going to do cosine. The cosine of 60 is equal to x divided by 7. Multiply both sides by 7, so I get x is equal to 7 times the cosine of 60. So if I plug that in the calculator, or if I remember my special right triangles with 30, 60, 90, this is actually going to be 7 times 1/2, or 7 halves. In the y component, same idea, this is opposite side here. So we're going to do the sine of 60 equals y over 7. So I multiply both sides by 7 here. Y is going to equal to 7 times the sine of 60, which if you remember again, that is going to be √3 over 2 as a special right triangle. So my y component here is 7 √3 over 2. As a vector, we put these together in our components. My x component is 7 over 2. My y component is 7 √3 over 2. Okay, so next one here, find the direction angle of 2, 9 to the nearest tenth of a degree. So we give us that vector p here is 2, 9. Doesn't matter where I model it, but if I just usually just start them at the origin like this, it's going to go 2 to the right, 1, 2, 3, 4, 5, 6, 7, 8, 9 up. Okay, so this is vector p here. So if I want to find my direction angle, I got to remember that this is going 2 to the right, and 9 up. So my direction angle is just the theta that makes it's being made there. I'm modeling it as a right triangle. So if I look at this as opposite and adjacent, that's going to be a tangent. So if I do the tangent of theta, that is going to be my opposite divided by my adjacent. So that means my theta is equal to the inverse tangent of 9 over 2. So we just plug that in the calculator. So we get 77 point, and we're going to round it off to the nearest 10th degree. So 77.5 degrees here. All right. Find the direction angle of this vector here. R is negative 7i plus 2j to the nearest 10th of a degree. So same thing as before. My components are negative 7 and 2. So I'm going to say it's going to go negative 7, 1, 2, 3, 7 to the left, and then 2 up. So here's my vector right there. Okay, so that's R. Now the theta, the direction angle, is going to count it from here. We always count them from going from the terminal side, just like with our unit circle. So this is my actual theta that I want to find. But in order to get that, I'm going to have to use my reference angle here. So I'll call it theta prime, I guess. So if I again set it up with a tangent in this case. Okay. So I'm going to model this with a tangent. So I've got in my X direction here, it is going 7, and in my Y direction, it's going 2. So that means I can set it up with, if I were to say the tangent of my reference angle, theta prime, is equal to opposite 2 divided by my adjacent 7. So that means my theta prime here is going to equal to the inverse tangent of 2 over 7. And so when I do that, I get a theta of 15.945 degrees. So that means if I want to find my actual direction angle, I'm going to subtract that from 180. So just like using with our unit circle stuff, we can do 180 minus my 15.945. And that's going to give me 164.1 degrees when I round it off to the nearest 10th. Okay. All right. Next one. We have, 2 more examples to talk about in terms of word problems. So here's another way we can do our word problems in terms of our motion when the multiple vectors are happening at the same time. A soccer player is running forward at 7 meters per second, kicks a soccer ball with a velocity of 30 meters per second at an angle of 10 degrees with a horizontal. Was the resultant speed and direction of the kick? So the idea is that we're going to combine the two things, the soccer player running and this person's kick of the ball. So for example, if I call my soccer player a vector, this person is going to the right by 7 here. Okay, so 7 officially meters per second. Then kicks the ball, so their speed is also going to kick the ball, make that faster, but that ball is launched at this vector. Okay, it's going at 30 meters per second at an angle of 10 degrees with the horizontal. Okay, so what we get is a resultant speed and direction of the kick overall is going to be a combination of these two. So in order to do this, the first thing I want to do is I want to break down my kick into a horizontal and a vertical component. Okay, so just like we did before, if I do my vertical or my horizontal, that's going to be related to cosine here, just like last time. Oh, 1 second here. Okay. So we're looking at the x component is going to be related to cosine like earlier. So it's basically equal to my magnitude times the cosine of my angle. That's a little shortcut we can do with that. So my x component comes out to 29.5. And in this case, I guess I could write meters per second. So that is representing the horizontal motion of the kick. In the y component, that is going to be right here. Y is going to equal to 30 times the sine of 10. So if I do that, that comes out to 5.2. So the resultant, like if I think of it this way, my first vector is traveling 7, 0. My second vector is at 29.5, 5.2. So I need to find the magnitude and direction of this. So two things, first thing I want to do is find the magnitude. So with the magnitude, remember, that is equal to the square root of what's going to be my component squared. Sorry, I should have wrote this down. The resultant vector, if I combine my two x components, that comes out to 36.5. And if I combine my two y components, it's going to be 5.2. So what's happening is the soccer ball is actually traveling in this in the horizontal and this in the vertical. So now we can find the magnitude of that. So I'm going to do that by taking the square root of my component squared. So 36.5 squared plus 5.2 squared. Okay. So my magnitude of my vector here, if I plug this in my calculator, I'm going to get 36.9 meters per second. So even though here there is being kicked at 30 meters per second, because of him running, it's going to make it a little bit more of a speed. If I model very quickly this vector now, it's going to look something like this. Okay, it's 36.5 and 5.2. Meaning I could do for my theta, for my direction here, I'm going to do tangent. So the tangent of my theta is equal to opposite over adjacent. So my theta is equal to the inverse tangent of 5.2 over 36.5. So when I do that, I get my theta here is going to be at 8.1 degrees. So my resultant speed is 36.9 meters per second at an angle of 8.1 degrees here. Okay, last one, another one like this. Airplane heads due east at 400 miles per hour. So let me model that real quick. Here's my airplane motion going from here to here is 400. If a 40-mile-per-hour wind blows from a bearing of north 25 degrees east. So remember how we model that. That is going to be like this. If we start from the north, we go 25 degrees east, so it's going to look something like this. Okay, so it's coming from that direction, which means the actual direction and speed of that is going this way. So it's coming from that direction, so it's going here, making this also 25 degrees. Now, to help model that, so it's 25 degrees, it's going 40 miles per hour that way. Just like our previous problem, we want to find our x and y components. So if I look at that as x is this way and y is this way. So I can do this with my angle inside of this triangle now. 90 minus 25 is going to give me my 65 degrees. So using our little shortcut, we could take x component is equal to my magnitude, which is 40, times, well, in this case, we know we're going to be moving left with this wind. So I'm going to make it a negative 40 then in that case. So negative 40 times the cosine of 65. So my x component comes out to a negative 16.9. For my y component, same thing. We're going south comparatively, so we can call that a negative direction. So negative 40 times the sine of 65, which comes out to a negative 36.25. So we have our two x components, so that means our resultant vector. So we got this vector is 400, 0. This vector is negative 16.9. Oops. Negative 16.9, negative 36.25. So from there, my resultant vector, if I'm going positive here and then negative here, we're going to subtract these two, or I guess just combine them, but we're going to end up subtracting them. So it comes out to a resultant of 383.1. 0 minus this is just a negative 36.25. So the actual path of the airplane is not going exactly east. Instead, it's going to be made up of my horizontal component going 383.1 to the right, to east, and going south 36.25. So this is what we're trying to model here. So we want to find that. So just like last time, we're going to find our magnitude. So we'll do magnitude is equal to the square root of my component squared. So 383.1 squared plus technically negative 36.25 squared. So I plug that in my calculator and I get 384.8, and this is going to be miles per hour. We also need to find the angle that we're traveling at. So this angle here is going to give me my, if I look at that one, so we got this angle is going to be, where am I at? Sorry. That's going to be tangent again. So if I do I'm just going to go right to my inverse tangent. It'll be the inverse tangent of 36.25 divided by 383.1. So when I do that, I get 5.4 degrees. Now keep in mind where that is. So when we label this, we want, let's see here, in the direction of the plane. So we want the ground speed and direction of the plane. So it's 5.4 degrees, but we have to describe this correctly. So based on how we've done this, I would describe it as the plane is traveling at 384.8 miles per hour at, we're going to go east 5.4 degrees south. So we're from the east direction, we're going south 5.4 degrees. So that would be my final answer for that one. All right, and that's actually it for today. Again, we're just working with our different components and how we can combine things together. Just keep in mind that sometimes we're going to subtract our components or add the components depending on what the scenario calls for. All right, that's it for today. Take care, everyone.